We can start. Uh, this is class discussion. So this is on the summary. Okay. So let me just get to. So the first part of our lecture, we learned on polymers in brief introduction. Then the polymers, you could also say that it is a repetition of macromolecules, and it will create a long chain, really long chain, and of course there's some difficulty when we control the length. So you can imagine like a noodle, like I mentioned. Maybe over add here. Later, these nodes, all the nodes, I will put into the Moodle. So don't worry about the nodes. So this can be written like a noodle. And because its property itself, like a noodle, it will entangle. Okay? So the consequences, the impact on the long chain is making all the segments become entangled, which reduce the chain mobility. Okay, the chain mobility. And also the chain mobility, how they affect the entanglement, is due to there are some special temperature we call the glass transition temperature that will affect the mobility when it's entangled, and then when the temperature is increased, it's become like a rubbery and it's easier to be stretched, and because of that, the implications is the polymer has a viscoelastic property, which is a combination of liquid and solids. Maybe I haven't really told you at the beginning that people at the early introduction of the polymers, like maybe before 1920 or 1930, they thought the polymer is like a colloid, and that's different, right? So people think, oh, maybe this is a colloid, but that's the difference because of the macromolecules that the polymer has. So they have this kind of property that's similar to the colloids, right? Similar. And then we know that aside from the viscoelastic, the liquid and solid, and because of they have the special temperature, the glass transition. Then another implication is that the polymer is a semi-crystalline. We can say semi-crystalline, and we can adjust like how many portion of the amorph that may be larger, or maybe crystalline that is larger, and it will affect the property of the polymers. The easy property that we can think is the mechanical property. Whether the material or the polymer is brittle or rigid enough, or maybe it's going to be easily to be stretched like a rubber. Okay. Okay, this is just a review from a last class. Okay. And then we look at the mechanical property. It will be very diverse. You can make it a rubbery, make it rigid, and it's easy to manufacture. Cheap and easy. Easy means how to process, the energy is really low energy. And then another advantage is most polymers are lightweight materials, which means that we can substitute to other equipment that is usually with heavy weight, and we can substitute with the polymers. Okay. But the disadvantage, of course, is the thermal property usually low. It easily break when you have some solvent. Okay. And the most important thing is it's produced really huge amount of waste. So that one thing that we can think of this waste is maybe producing more biodegradable or increasing the biodegradability of the polymer itself. Okay? And there are several sectors that we can think on polymers: packaging, clothes, like your clothes. There are polymers, fibers, protection, like for armor and electronics also. A super absorber like diapers, that's also special polymers. Photolithography is for semiconductor. And then we can categorize the polymers as a typical by looking at the modular architecture. You can have a linear branch, network, hyperbranch, or dendrimers that is specially a pattern, which is going to be the polymers will nucleate like a dendrit in a cell, right? And the molecular we can also think as the stereoisomer. If you remember the cis-trans, the geometric isomer in chemistry, we can also think the architecture like that. But this is the general one, okay? I think this is enough. And then the order of polymers, the order of monomers in polymers, we can have the homopolymer, which is the same monomer in every sections, and we can have also the random. We have more than one. We could add another one, maybe C, maybe D, okay, maybe more than 2 units for the monomer. It can be alternating, like AB, or AA, is also alternating. Or block, like one block, one monomer, another block, one monomer. And graph, one monomer as a main chain, and another monomer as a branch. Okay? And why people develop this kind of polymers? Because sometimes this type of polymer, especially for block and graph, this will easily adjusted. If we can react with other polymers or other monomers, we can maybe change this and then put into another polymers, and it's easily to be used as a synthesized materials. So that's why like many chemical company, especially if they are producing the synthetic polymers for a synthesis. So they produce polymers for synthesis. Like if you go to maybe some lab that's doing experimentation, they usually buy some chemicals. Of course, the chemicals is needed for synthesis, and there are company that selling those chemicals. Okay? So sometimes they provide you with some certain. Do you want to have a block or graph or maybe any other polymers as well? Okay. If you need like a synthesis, okay. We will learn about that on, I think, the process on how we make polymers, because there are many processes like a synthesis, or even some polymers they just need to be like a blending. So I think we will need this. Sometimes we just need to have a blend, just increasing temperature, just put the polymer pellets like the thermoplastic, and then this will be processed. And we can make any shape we want. Okay. Another perspective is we can make the classification from the material property in general. I already said about thermoplastic, right? Thermoplastic. This is from the property itself. We can classify becomes 3, the thermoset, and the rubber or elastomer. And then we can also classify it with the crystallinity.
amorphous or semi-crystalline. And from the semi-crystalline, we can also make a fiber if we reoriented the orientations. We can take this as a fibers like that. And then by origin, where the polymers come from. Okay? Usually, what we are going to elaborate in our course, mostly about synthetic polymers, right? But we can also have a polymers that has inorganic materials. So we can say it is inorganic polymers. Maybe sulfur or silicon or phosphorus. Okay? Sometimes you will see this element in the polymers, and we say that, okay, this is inorganic polymers. Okay? Also, the origin is just like in nature, natural. Okay? Or we could say this is a biopolymers. Like a collagen, hyaluronic acid, what else? The chitosan, what else? The cellulose, they are biopolymers, the biopolymers, okay? And the synthetic one, we will learn more on the synthesis, okay? So mainly we have two, the step growth and chain growth, polymerization. Okay? We will learn more. I think today I will introduce just a really brief for the synthesis, okay, what's happened inside and what kind of description we are going to we take. And then next week we focus on the step growth. Focus on the step growth. Okay. Okay, so now if we take the classifications for polymer reactions, let me start from here. So classification for polymerization. So the first person to describe the reactions is the characters. If you remember the history that I mentioned in the early class. So it was based for years based on the characters experiment. It's based on a comparison on the molecular formula of the polymer with the monomer itself. Okay, so ethylene becomes polyethylene. Okay, from that perspective. Okay? So characters defines that first, and then through that reactions, there will be first we say there will be a condensation. Okay? There will be condensation. So how to know the condensations? We know that from the atoms of the repeat units. So the repeat units will have fewer atoms. If you compare with the monomers. This is because in condensation there will be some elimination, usually water. So we react and the byproduct is water. Okay? So we eliminate a small molecule. It can be water, it can be some acid, usually H2O, HCl. There will be this small molecule. We will see later on. So this is we call the condensations. Okay? And then we also have, okay, so characters, he discovered, oh, there will be some condensation, but he also get that, oh, we have, we call it addition, okay, addition polymerization, which the difference from the condensations in terms of the word itself, we are not yet going into the reactions, and later we are going to reactions, but the definition itself, one we call before is condensation, and this is addition because the number of the atoms. Okay? But for addition, it's just we add something. We add. Then we just add something, and what does that mean is the repeat unit is identical. Okay? The repeat unit is identical to the monomers. Okay? So this is the difference. Okay, so this is identical with the monomers. The previous one, they eliminate the small molecules. But how they form, basically similar. So they add, for condensation, they will eliminate small molecules. But for this one, just add, slowly, adding slowly. So the condensation and additions, we usually say that is part of the step growth polymerization. So let me write here, step growth. So we have the condensation process and addition. Okay. But before, so when characters found, he just found and defined by, okay, we have the condensation, polycondensation, and we have the addition. Okay, we have two. But he doesn't know. Later on in today's era, the polymerization is based on step growth or chain growth. The chain growth haven't really get into the idea of the characters. So characters still think that, okay, polymerization is just two, the condensation and addition. Okay. And then later on, the classifications, the condensation and addition is not satisfactory. Okay? It's not satisfactory. So because they found the chain growth. Okay? So the better way to classify, okay, is based on the mechanisms, how they react and how they define the monomers, each monomers process reaction. Okay. So we can say we have step growth and chain growth. Okay. So these two is ideal to describe most of the polymerization process. There are other processes like a ring opening and etc. But most of the polymers is getting the step growth and chain growth. Okay. As you see from the word step, like you can think like a step by step, one, and like that. But chain growth is more like a chain. It's like when you react, it's become a chain. So there's a lot of reactions there at one time. But for step growth, one time one, a little bit slow. But chain is really fast. It is just a brief introduction. Okay, we'll see how fast it is. So, but again, in step growth, like I said before, there will be a condensation or addition. Okay. So as you see from the definition, the polymer chain grows stepwise by reactions that occur between any two molecular species. Okay, so it's like stepwise. So step by step. So as you see from the chain growth, The key component of the chain growth is the reactive end group on the growing chain that is making the reactions faster than the step polymerization. So if we see from this part here, okay, so if the O here is like molecules, the monomer molecules, and you see I here, this I is for initiator. So if we see from this part, okay, maybe you could just take dimer or trimer or maybe spectromer just to describe if you want to take notes. Okay? Not need necessarily to write all of them because they are basically similar. So if you see the step polymerization, we polymerize two different monomers, okay? And then make it reactive, and then at the end they will polymerize. For the chain polymerizations, usually we need what we call the initiator. Okay? We need initiator. Initiator can be anything, but the idea of initiator is the initiator is making one of the sites reactive, one of the end group reactive, and because of the reactive, then it will create chain. It will create chain. So initiator will react with the monomer. It will make like a molecule that has a reactive end group, which is in this initiator. And this initiator will add with other monomers that will create a chain like this and making long, really long. Okay. Okay, that's the idea. So you can see if you want to see, I think it's better from the picture. But if you want to see how the reactions like described, the step growth. There's one, I think this is also important. The degree of polymerization, this will increase slowly after reaction. So after reaction with monomer, increasing because it makes more easily to polymerize with other monomers as well. Okay. So all polymer chains continue to grow as the conversion of the functional groups and the chain lengths increase. So it will finally, but I think the most important thing, the degree polymerization increase slowly, and then the monomer is actually like consumed in a large portion at the early stage. I think we can see it I think later on the reaction. But the chain growth at the beginning, it's already high degree polymerization, okay, because of the initiator. And the conversion is low monomer conversion, okay? And the monomer, it was consumed steadily. So maybe this one here, maybe this the monomer steadily consumed one, and then another one, it's easily. But here maybe for the step growth, the first time a lot of monomer is consumed, and then after that not that much, okay? And because of that there will be because at the early stage, maybe this is important. At the early stage, because of the monomer consumed largely, they take times. Okay? They take time because this consumed early. Okay? So because it's rapidly consumed at early stage, so slowly react at early stage. Okay.
But for the chain growth, the consumption for the monomer is just at the steady process, so the same time. So after the growth initiated, and this will happen, will be rapidly added. The monomer will rapidly added to the chain. Okay, so chain forms rapidly by the sensitization of molecules to the reactive site. The reactive site is this one here. Okay.
This is reactive site. Okay, so that's just a glance different on step and chain. Okay, and then another thing for reactions. So before we see that the monomer is react, right, and the structure is also, we can adjust, we can prepare the synthesis materials, right? And the one that is affected the reactions will be the functionality. So the monomer will have a functional groups, right? Functional groups, and usually those functional groups will affect how the reactions will be, and can especially for step polymerizations, because we need to think one monomer and maybe the other monomer, can we react this? So we need to think how to react those two monomers. So how do we do that is based on the functionality. Okay? Based on functionality. So what does it mean is actually relate to how many links? Okay, how many links? Okay. So if this is a chain, okay, how many, or maybe just a small chain, how many links that can be reacted? Maybe here we have one, maybe here we have one, and maybe we can use these two. Okay.
And we say, okay, functionality is 2, because we have potential links that is 2. But sometimes it is not necessarily equal to the number of the functional group present in the monomer. So the one that we need to think is not the functional group, but the functional group that will link. That's different. Because sometimes functional groups not react. We need to make sure the functional group will react.
Okay. And later, I'm trying to describe as much as possible, but probably will not be too details. Okay, because there are many reactions, but I will focus only with the one that is essentials, like the polyethers, the nylon. Okay, and that is for the step 1, the step polymerization. Okay, this is I think
we have seen this before in the early class, but this is basically the step polymerization. You see the propylene, ethylene, propylene, ethylene. We can react this and make it polyethylene, polypropylene. Okay.
This is all step polymerizations. This is also step polymerizations.
But I think the one here is addition.
One is addition, one is condensation. Okay. I think we'll go back to this part later on. Okay. Just idea. Okay. Okay, so the first 7, when you see the C1, usually this will be chain polymerizations. Okay? It's contained by the olefinic monomers. This is double one, and they have the functionality of 2. And then the other one, the number 8. Number 8 is ring opening. Number 8 is this ring opening. So we will get rid. So we will break the link. So we call this a ring opening. It's not step, not chain. It's another type of polymerization. So the first 7 is the chain. Okay, if you see here. If you see here, also chain. So another one. Step polymerization is the last two. The last two is this one. Okay. Ethylene glycol and terephthalic acid. Okay, so if you see from the table, for the step polymerization, it needs, I think number 9 here, for the ethylene glycol and the terephthalic acid, this will be one of the common reactions and I think essentials for polyethylene terephthalic. I'm not sure I had the video, but I think I will check later and will be at the behind. This will be you'll see we have the 2 diols, right? We have 2 alcohols, and when we react with the terephthalic acid, later you will see that this alcohol is gone, right? It's gone. It was supposed to be releasing water. It will make small molecules of water. Okay? So usually, in the step polymerizations, we need to have some temperature to evaporate the water. But maybe around maybe 80 to 300. That's the ideal temperature for the step polymerizations, because they will, if they are doing some condensation, they will release some molecules. The molecules usually are liquids that need to be evaporated. So usually we need to have a temperature for this polymer. For the number 10 here is also one of the essential reaction, which is nylon. So nylon, you see from this part here, how we name the nylon is based on how many carbon in this side and how many carbon in this side. So it has 6 and 10. So we say the nylon is nylon 610. There are also other nylon like nylon 66. Okay. I'm not sure whether the nylon has some other terms. I'm not sure if you check your clothes, maybe they will mention nylon something, but I think not really the chemical name. Maybe just the name, commercial name. Okay, so it's supposed to be, first is having the one side having the nitrogen, diamine, and another side is having alcohol, and not alcohol, the acid, carboxylic acid. And the other part, like from the first until number 7, if you see clearly from this part here, all of them having the double bond, right? Double bond. Okay. So imagine like like we have in the previous page earlier, I said that we need to have like an initiator, right? Initiator. So initiator, this will react to the monomer. Okay. to do that, how they can react. Okay, it's based on different electronegativity. Okay, usually it will be having maybe more electrons here, okay, and it will react. And that is probably, if you see from here, probably that is the reason the double bond is broken. Because they will attack this double bond, it's broken, initiator will come, and because there is the initiator, it will also react with another monomer, and they will do the same thing, and they will make really long chain at the small amount of time. I think there will be in the chain polymerizations. Okay, that's functionality. Okay. So if you see from this part here, we see how we have. So for example, the linear polymerization. From the previous example, or maybe some example from previous course, if we have the functionality 2, mostly they will become easily become the linear polymerization. But if the functionality greater than 2, the link is greater than 2, the functional group that can link the other one, perhaps this one. Okay. You see, it has 3, so it can be branched. So aside going here, it will also going other way around. Okay. And you see from here, it's also 3, going 3 like that, and 2 with 4, it's also going to have a hyper branch. So difunctional, trifunctional, tetrafunctional, it will affect the branch formation. And perhaps maybe if you look and if maybe complex enough, maybe making a network. And then the reactivity, the reactivity. So the chemical reactions is they will occur or proceed because of the collisions between the reactive functional groups. So this is just to make sure that, or to confirm that the one that makes the polymerization is really affected is because of the collision of their functional groups. Okay. So we need to make sure that all the functional groups collide. So the reactivity depends on functional group collision frequency. So the longer collision is, then the polymerization will be make sure. Remember, the polymer at the end, it will be an entanglement of the macromolecules, right? The entanglement of macromolecules. So we can think of how they become like that is because of the functional group that is collide, and then they react and make start polymerization. So when we try to deal with the synthesis, we need to make sure that all of them, in the percentage or the possibility, we need to increase the possibility that these functional groups collide, frequently collide. And if we increase the molecular size, then the diffusions is decreased. So this is also important if we want to make sure that the functional groups is collide each other. The reactive functional groups is collide, which means we need to make sure that it makes link. Okay, it makes link. So how to make sure that? One thing is we need to think on the molecular size. What is molecular size of our monomer? Can we make the monomer, for example, if the diffusion decrease, then how it will be moved is also decreased, right? The motion is decreased. Right? And then the effects is the time. Okay? How long the monomers will meet. It will affect. So molecular size will affect. So this is also another thing to adjust. Can we make sure the functional group react? How to make sure of that? Perhaps from the molecular size. Okay? But then, actually, our thinking, then previously the molecular size, but then the reactivity is not depends on the molecular size. So our thinking may be wrong. So there is one principle here, which is called the Flory principle. If you want to know more, maybe you can Google later. What's Flory principle? This is just a small introduction. It's equal to reactivity of the functional groups that first assume its intrinsic reactivity of functional group is independent of molecular size. But that's Flory principle. And it's not affected by the reaction of other functional groups in the molecule. So if you have like more than one functional groups, so the one that is reactive is the one that is really our concerns. Okay? So our concern is just one that has a reactive. Okay? So there's one problem here. If you want to check, maybe I will discuss this next Monday. You see, polymerization of phenyl chloride produce polyphenyl chloride. High molar mass at low monomer conversion, where the other polymer is react from ethylene glycol with terephthalic acid. This one. Okay. So the phenyl chloride is number 6 here. So the ethylene glycol and terephthalic acid is this one. So that's for PPC and PET. Okay? And for each polymerization, explain what the observations indicate in terms of the type of polymerization taking place. Okay, I will start to discuss this, I think, next Monday. So I will stop until here. And we will discuss more on the reactions on Monday. Okay. So any questions? Any question? So I think you can maybe look up the Flory principle, how they can relate to the reactivity of functional groups. And then if you want, you can also see these two reactions. And by the way, as I mentioned, okay, I really hope you can, this is not, okay, you can go here, the macro Galeria. I already put the link in the Moodle, but I think no one searched this. Macro Galeria is basically all the basic information of polymers that you can learn. You can set from level 1, level 2, level 3, even for the three-dimensional models. For example, if we look on for example, the level 2, okay? So we can have all the polymers that can be learned. For example, the nylon. They have all this three-dimensional models, the structure if you want to draw, and we can play with this, like we can spin this, and this is basically the 3D that I will maybe tell you more about this in the next Monday class. But basically, this is how the standard of the 3D models of the polymers or biochemistry. See the color different? It will be related to which one is hydrogen, which one is oxygen, which one is nitrogen, okay? And which one is the carbon. Okay? I think this will be next week. I will tell you about this website. This website is really good. It's free and you can like learn anything about polymers, mostly the basic information. Okay, you can just Google macro galeria, or you click the, I think the Moodle maybe